Section 1. The Recipe of Chemistry. A Real-World Introduction. Imagine you are in your kitchen on a quiet Sunday afternoon, ready to bake a batch of your favorite chocolate chip cookies. You pull out a trusted recipe card, passed down through generations. It calls for very specific amounts of ingredients: 2 cups of flour, 1 cup of sugar, 2 large eggs, a cup of chocolate chips. You instinctively know that following this recipe precisely is the key to success. If you were to use only half a cup of flour, your cookies would spread into a thin, greasy mess. If you forgot the sugar entirely, they would be bland and unpalatable. Careful measuring, this adherence to ratio, ensures a predictable and delicious outcome every time. This fundamental principle extends far beyond the kitchen. It is the very heart of what chemists do every day in laboratories and industrial plants around the world. In chemistry, atoms and molecules are the ingredients, and reactions are the recipes that transform them. The science that provides this recipe, telling us exactly how much of each chemical we need, is called stoichiometry. It is the rulebook for chemical cooking, ensuring desired yields without wasteful excess or disappointing shortfalls. Section 2. Defining the Blueprint. What is stoichiometry? It is the branch of chemistry that deals with quantitative relationships between reactants and products in a chemical reaction. Think of it as the accounting department of the chemical world. It meticulously tracks all atoms, ensuring what goes in is accounted for in what comes out. Stoichiometry rests on the law of conservation of mass. Matter is not created or destroyed. Atoms are rearranged. Stoichiometry is the mathematical embodiment of this law, proving reactant mass equals product mass. Its applications span life-saving medicines, advanced materials, fuels that power our cars, and fertilizers that grow our food. Without it, chemistry would be guesswork. With it, we translate plans on paper into tangible substances. Stoichiometry lets us design processes, optimize production, and use resources efficiently. It moves chemistry from descriptive to predictive, turning textbook reactions into real-world manufacturing, the blueprint that guides chemical construction. Section 3. The Chemist's Dozen. Understanding the mole and molar mass. Counting atoms one by one is impossible. Scientists define the mole, a counting word, like a dozen. 1 mole corresponds to Avogadro's number, 6.022 x 10^23 particles. This links the invisible microscopic world to the lab bench. We measure mass with a balance. The mole converts between particle count and grams we can weigh. Instead of atoms reacting, we think in moles reacting. Molar mass is the mass of 1 mole of a substance in grams per mole. For carbon, atomic mass, 12.801 U corresponds to 12.01 g mole. For compounds, some constituent atomic molar masses. Water, 2x 1.01 plus 1600 equals 18.02 g mole. Weighing 1802 g of water gives 1 mole of H2O molecules. Master the mole and molar mass to move seamlessly between atoms and grams. Section 4. The Art of Balancing Chemical Equations. A balanced equation is the foundational recipe and must obey conservation of mass. Adjust only coefficients, never subscripts, which would change the substance. For example, H2O is water, H2O2 is hydrogen peroxide, a different compound. Consider combustion of methane. CH4 plus O2 yields CO2 and H2O. Inventory atoms: balance carbon, then hydrogen, then oxygen. Place a 2 before H2O to balance hydrogen, then a 2 before O2 to balance oxygen. Balanced: CH4 plus 2 O2, CO2 plus 2 H2O. Now it is ready for stoichiometric use. Once balanced, an equation unlocks its mole ratio, the most powerful stoichiometric tool. Coefficients represent proportional moles of each substance. They form conversion factors, such as methane to carbon dioxide 1.1 and oxygen to water 2.2, which simplifies to 1.1. To relate methane to water, use 1 mole CH4 to 2 mole H2O, written as 2 mole H2O over 1 mole CH4, or inverted as needed. Set up so units cancel, leaving your desired substance. Never skip. Convert mass to moles. Apply the mole ratio. Convert moles back to mass. The mole ratio is the non-negotiable heart of every stoichiometry calculation. Converting between moles of substances is the core logic that makes all other calculations possible. Now, a complete mass-to-mass problem from start to finish. If we completely burn 32.0 grams of methane, how many grams of water are produced? Use CH4 plus 2 O2, CO2 plus 2 H2O. We will need molar masses. Methane, 16.0 g mol. Water, 18.0 g mol. Step 1. Convert given mass to moles using N equals mass divided by molar mass. 32.0 divided by 16.0 equals 2.00 moles of methane. Step 2. Apply the mole ratio. 1 mole CH4 produces 2 moles H2O. 2.00 times 2 equals 4.00 moles of water. Step 3. Convert moles to mass using mass equals moles times molar mass. 4.00 times 18.0 equals 72.0 grams of water. Answer: burning 32.0 grams of methane produces 72.0 grams of water. Recap: grams to moles, moles to moles, moles to grams. Follow these steps to solve any mass-to-mass stoichiometry problem. In real reactions, reactants are not always mixed in exact stoichiometric ratios. The limiting reactant is the ingredient that runs out first and limits product formed. Analogy: if a sandwich needs 2 slices of bread and 1 slice of cheese, 10 slices of bread and 3 slices of cheese make only 3 sandwiches. Cheese limits. Bread remains in excess. Procedure: for each reactant, calculate how much product it could make. The smallest result is the limiting reactant and the true theoretical yield. From hydrogen, 6 mol H2x, 2 mol H2O, 2 mol H2, just 6 mol H2O. From oxygen, 4 mol O2x, 2 mol H2O, 1 mol O2, just 8 mol H2O. 6 is smaller than 8, so hydrogen is limiting, and the maximum water is 6 moles. Stoichiometry gives the theoretical yield, the maximum possible amount under perfect conversion. Real experiments face incomplete reactions, side reactions, and handling losses, so actual yield is usually lower. Percent yield equals actual yield divided by theoretical yield times 100%. Example: if theory predicts 72.0 grams of water, but you collect 64.8 grams, percent yield is 64.8 divided by 72.0 times 100. Result: 90.0%. In labs, that is very good. In industry, processes strive for yields near 100% to maximize efficiency and minimize waste. We unpacked stoichiometry as a logical, step-by-step recipe for chemistry. A balanced equation respects conservation of mass and provides the mole ratios. The mole is the counting bridge between atoms and measurable grams, powered by molar mass. Solve mass to mass. Convert grams to moles. Switch substances by the mole ratio. Convert moles back to grams. Account for limiting reactants and percent yield to match real lab outcomes. Remember, stoichiometry is chemical accounting. Balance your equation, use the mole to count ingredients, and use ratios to figure how much you can make. From baking cookies, to manufacturing medicine, to launching rockets.